Hi everyone. So today we are going to discuss what is a Symmedian, and then I'm going to explain to you the various theorems that are required to understand Symmedians, and finally I'm going to apply these theorems into a Olympiad problem and show it to you. Okay, so let's get started. So what is a Symmedian? A Symmedian is the reflection of a median in the angle bisector. Okay, so let's see that here in action. So if a median, you see the median AD, it's reflected in the angle bisector to get this blue line, which is the Symmedian. All right, so let's actually write it out. So as a proper definition, now this particular definition that a Symmedian is essentially the reflection of the A median in the angle bisector can be written in terms of angle conditions. Okay, so in fact the angle conditions are pretty easy to understand, because notice that since it's a reflection, these two angles are equal, and since the dashed or the dotted line is basically the angle bisector, these overall angles are equal. So if you subtract, these two angles must be equal. So that's the condition. Okay, so we can state theorem 0 the utility of this essentially is that we now have an angle condition, okay, for Symmedian, and we can use this to chase angles. Okay, so that's the benefit. All right, so now let's find another characterization of Symmedians. Before that, we need a little bit of preparation. So we should know what antiparallels are. So here's a sort of a definition of an antiparallel. An antiparallel is a segment, as you can see, G dash H dash in this drawing, okay, intercepted by the triangle with the property that this angle here is equal to this angle here. So in other words, this angle is angle C, if we call this angle C, and obviously that would mean immediately that if we call this angle B, then this angle would become B. Okay, now another way to say that is, notice that since here the exterior angle is equal to the interior opposite angle, okay, this would mean that this quadrilateral is cyclic. Okay, so basically the cyclicity you can consider is with BC, so this is A-antiparallel. All right, so one of the nice things to notice is that if you try to draw all the A-antiparallels, they are actually parallel to each other, because notice if you try to draw another A-antiparallel, by this condition this angle should be C and this angle should be B, but then these would become corresponding angles, and therefore you have these two lines which are parallel. So the locus of all the A-antiparallels are a bunch of parallel line segments. Okay, so that's what A-antiparallels are. All right, so with this let's see what is the connection to an A-symmedian. All right, so here's the observation. If you pick any point, if you take G dash H dash and you reflect it in the A angle bisector, then you will actually get a parallel line. The GH would be a parallel line. The reason is pretty simple. That is, when you in fact reflect a G dash H dash, you could consider reflecting the entire triangle AG dash H dash, and because under reflection this angle and this angle will be the same. Notice that this angle was seen the definition of A antiparallel. Now after reflection this would be C, and similarly this angle was B, right? After reflection this angle would be B. So what it means is that after reflection the segment GH that you get, right, that would be essentially inclined at an angle C and B here, which means that GH is parallel to BC. All right, now we know that the median always bisects any parallel line segment. Okay, that we know. You can get it from the converse of midpoint theorem if you like, right? So you essentially know that the median bisects. So when you reflect the median about the angle bisector, then the Symmedian will actually bisect the antiparallel. So here's the theorem. The A-symmedian, all right, so if you draw, what that means is if you draw a parallel line to G dash H dash, you again have the A-symmedian passing through the midpoint of that A-antiparallel. Okay, so the locus is the locus of all the midpoints. All right. Okay, now this particular characterization allows us to give a length or a ratio characterization of Symmedians, which is very useful to do computations with length. Okay, so here is theorem 2. So theorem 2 is about ratios of length, and in fact we will use what we just now proved. So pick a point P on the A-symmedian. Okay, now draw an A antiparallel passing through it. Let's call it G dash H dash. Then if you drop a perpendicular from P to AB and you drop a perpendicular from P to AC, okay. Now notice we already know the angles. We know this angle is angle C and we know this angle here is angle B, right? We know this already. Alright, so now that would mean the following. The distance of the point P, right? If you take a point P on the A-symmedian, okay, then the distance of the point P to the line AB, the perpendicular distance, when I write D off, I mean perpendicular distance from P to AB divided by the perpendicular distance from P to AC. If I try to calculate this, notice this perpendicular distance can be computed by a trigonometry. So if you take this perpendicular distance in this right angle triangle, notice this right angle triangle, you know this is angle C and this is PH dash, right? So you can write PH dash as the hypotenuse, so therefore you can write PH dash, okay? So you just take this segment, the length of the segment PH dash into sine C, because notice that this is the opposite side of this right angle triangle, this opposite side to angle C in a right angle triangle, and the hypotenuse is PH dash. Very similarly, you can write PG dash by sine B, okay. And what is PH dash and PG dash? Notice that you can cancel PH dash and PG dash because we proved that P is the midpoint of G dash H dash in our earlier theorem, right? Theorem 1. So simply now we get a nice characterization that it is sine C by sine B. This is the trigonometric characterization itself that is useful. If you want further, you can multiply by 2r the circumradius and use sine rule to essentially write, let me push this diagram a bit, it's getting a little congested here. So okay, all right, so let me write this as C by B. So what this proves is you have the following theorem. Okay, so if you want to check whether a point P lies on the A-symmedian, all you have to check is whether the ratio of the perpendicular distances is the ratio of the sides, okay, the corresponding sides. Notice that this side C is essentially this line segment and B is basically the length of this line segment, okay. Now the converse really follows from the fact that you know, the ratio of perpendicular distances, the locus of ratio of perpendicular distances uniquely determines a line, okay. All right, so now we have basically another characterization of the Symmedian, and that is in terms of ratio of distances. Now this theorem will be used to actually prove a very famous configuration in which Symmedian arises. Okay, so let's do that now. This is the final theorem that I'm going to show in this video. So what is the theorem? This theorem is actually giving a configuration which you have to memorize. Okay, it's a very nice configuration. It says the following. You can locate the Symmedian commonly in such a situation. That is, if you take a triangle, and you draw its circumcircle, okay, then if you draw the tangents at B and C, if you draw the tangents at the vertices B and C and you extend it to meet it at some point P, then AP is in fact the A-symmedian. Amazing, right? Okay, let's see why. It's not hard to prove at all. All right, so that's what I've written in theorem 3. So let's extend this line segment AB as much as we can and try to use theorem 2. All we have to do is compute the ratio of the perpendicular distances, right? So let's do that. So let's actually drop a perpendicular. Well, hopefully it looks as perpendicular as possible. And let's draw another, assume as perpendicular. Okay, so let's again call this X and Y. All right, now all we need to do for this is a bit of angle chasing. So what we need is what's called the alternate segment theorem. Notice that when you have a tangent and you have a chord, then the angle subtended, angle between the tangent and the chord is equal to the angle subtended by the chord. This is called the alternate segment theorem. So this allows us to say that this angle C is actually transferred here. So this is what we called throughout angle C, green. This is C. Now by vertically opposite angle, this angle will become C. Very similarly, this is B. And by alternate segment theorem, this is B, vertically opposite, this is B. Okay, now you see that we have actually a right angle triangle here with one of the perpendicular distance is what we want, px, and one of the angles is angle C. Okay, so let's in fact calculate the ratio of perpendicular distances. So the distance of P, this point by the way is P, okay, distance of point P to AB, line AB, divided by distance of P to line AC is essentially nothing but, let's see, so Px by Py, right, that's the perpendicular distances. But by trigonometry you see that Px is really nothing but, notice that this is B and this is C, okay. So you get Pb sin C by Pc sin B, okay. Now notice that the tangents drawn from a point to a circle are always equal in length. That's a theorem we learned from school, right? So we can just use that to cancel, these two parts and write sin C by sin B, which, as we know, I mean, this was a trigonometric ratio that we wanted to prove, or you could write it as C by B, okay. So we proved that the ratio of perpendicular distances from P to AB and AC is in the ratio of the sides C is to B, and from theorem 2 we know therefore that P must lie on the A-symmedian. So AP is indeed the A-symmedian, okay. Now what is the use of this? So the use of this arises in many Olympiad problems, and I will share basically a list from Rayleigh. There is some nice problem set. However, I also recently solved a crux problem using that. So I'll also leave a link to the description of that problem and its solution on my blog, okay. Alright, so but before that, let's see an application of it, okay. So this is Polish 2000 Math Olympiad problem, in which they have given you a triangle ABC in which AC equal to BC. It's an isosceles triangle. If P is a point inside ABC with some weird looking condition, angle condition, that PAB, so let's mark it. So basically PAB is PBC, okay, it's given in the problem. Next, since it's an isosceles triangle, the base angles are equal. So if the remaining is a red angle here, so CAB is black plus red, the remaining on the right hand side also must be black plus red, so this must be red, okay. So which means we have the following situation. We have, by the converse of alternate segment theorem, notice if you draw the circumcircle of PAB, if you draw the circumcircle of PAB, notice that the angle made by AC is equal to the angle subtended by the chord PA. Notice this length and this length are equal. So which means that PA and CA and CB are tangents to the circle PAB, okay. The tangents to the circle PAB. Wait a minute, what does that mean? So let's actually draw the circle. So you have some circle here, all right. Now, if CA and CB are tangents, okay, and they meet at the point C, okay, then CP, just from configuration 3, we just now learned, I mean the theorem 3, sorry, we learned that CP must be the median, P median of PAB, okay. So CP is the P median passing through of triangle PAB, okay, because C is the meeting point of the tangents at the other two vertices of triangle PAB, okay. And once we have this, if we extend this line, then we know that from theorem 0, or rather the first characterization, that the symmedian makes the same angle with one of the sides as the median makes with the other side, okay. So we know that APM must equal, let's call this some x, then it should equal XPB, okay. Now notice that because CPX is collinear by construction, right? CPX is collinear implies that angle BPC plus angle XPB is 180, okay. But angle XPB is equal to angle APM and we are done, okay. So angle APM plus angle BPC is 180, You see, the problem was so simple using Symmedians. Okay, so I'm going to share a link to a very recent crux problem, okay, which I again solved by Symmedians. Okay, so please have a look. Bye.